Hey everyone. Sorry for the delay in getting this out. I was working for a long time on putting together the little study guide that I have linked in the description of this video. So be sure to take a look at that. I covered a lot of, or I wrote out a lot of what I think, was difficult for me in the course and things that I just felt like warranted a little bit more in depth, practical knowledge about. And of course, there's also just I've drawn out the cycles and all of the amino acids and the nucleotides and the sugars that you need to know, as well as the fatty acids and all of those cool things. So be sure to look at that, and keep in mind that it's not like the end all be all study material. It's not like you should just study that. You should study everything and then just use it as like a little something to go over before you take the test, or something like a little mental check to see if you just if you know the things that I'm talking about, or if you're feeling unsure about any of them, maybe go back and review that. So yeah, I hope that helps, and then I'll get into the past week's Action Center. So the first question, this was the very first question. I wanted to address some of the questions that I was asked the most about last week, and this was one of them. So we're synthesizing palmitate, and we're doing it with this purified fatty acid synthase. And so the acetyl CoA that we supply to this fatty acid synthase is this C3 H3. It's acetyl CoA, but it's radio labeled, and everything else is unlabeled. And so he's saying that, like, in this experimental setup, how many tritium atoms will be found. And so I actually circled it a little bit weird here, but the three belongs to that hydrogen. Tritium is essentially radio labeled hydrogen, so you can just think of this as a radio label. And so we're looking for where that's going to show up in the palmitate that we make. And so I've included the little diagram that he's provided in the slides of fatty acid synthase. And if you look at the cysteine of this sulfur right here, that's where the first acetyl group is going to add. And when it does, it's going to add from acetyl CoA. And if you follow this yellow block all the way down, it's right there, right there, right there, right there, and then at the end it stays on the end. And then there's a translocation of this back to that cysteine, and the cycle begins all over again. And so what that tells us is that no matter what we do to this thing, the acetyl CoA that we added is always going to be the last two carbons of the fatty acid chain. And that's something that you should definitely remember, especially for the exam. So I'm going to put a little star here. So acetyl CoA, when fatty acids are synthesized, are always the last two carbons. And so what that tells us is that, since we radio labeled the hydrogen as tritium, and there's three of them in acetyl CoA, then that means that it's going to be these three hydrogens that are radio labeled. And so, we'll find three labeled. I spelled that horribly. And that's our answer. All right. So next question is going to be about this. It's a beta oxidation question that we're asking about, how many ATPs can we produce per molecule of this 14-1, with a cis double bond on the 9th carbon that's metabolized completely to CO2 and H2O. And so it's very nice of him. He's given us the ATPs formed per NADH, FADH2, so we'll keep these in mind when we do this question as well. And so what I want you to think about when you do a question like this is normally, so you don't have to do this, but it helps me to draw out the fatty acid first. which is what I've done here. And I know immediately that I'm going to have to do something weird because there's a double bond. And so when I start thinking about a question like this, I know that it's a 14 carbon chain, so I know that I'm going to have to liberate 7 acetyl-CoAs, because there's 2 carbons in an acetyl-CoA, and a 14 carbon chain is going to give me 7 acetyl-CoAs. Now, the next thing to keep in mind is that, like, if we were doing this normally, then, like, based on your knowledge of beta oxidation and that pathway and how, the cofactors are produced there, normally what I would get is I would get 6 FADH2 and 6 NADHs produced. That's not the case here because of this double bond. And what happens when we have a double bond like that in a fatty acid chain is that we're going to actually reduce the number of FADH2s by 1. So we'll have 5 FADH2s instead. And this is actually, like, if you care about why, this is something that's, like, in the study guide that I made. It'll explain how exactly the enzymes work to get around the fact that this is kinked and this has a double bond. There's a different enzyme that you use there to sort of bypass a step, and eventually, like, what the consequence of that is you're skipping an FADH2 making step. And so now we can just plug these in and find how many ATPs we can make, and you should know from your knowledge of, like, the Krebs cycle and general metabolism that for every acetyl-CoA you can make 10 ATP. So these 7 acetyl-CoAs are going to go to 70 ATP. Now 5 times, our for FADH2, we've got 1.5 ATP produced per. So this is going to be 7.5. And our NADH will give us 15. All right. So once we add those together, we'll get 92.5 ATPs. But we're actually not done here because, if you remember, to activate the fatty acids, we'll need to lose 2 ATPs to do so. And so we're going to be subtracting those 2 ATPs from our net produced. So once we subtract 2, and we will get 90.5 ATPs instead of 92.5. So always keep that in mind, that you can't just, like, start metabolizing fatty acid without having to activate it first. Pay attention to especially those kind of questions on the test. If he asks you about fatty acid metabolism, pay attention to, is there a double bond? Pay attention to, has he told me to ignore the activation cost? Things like that. Like, be sure to know how many carbons you're dealing with. I know it's a lot to think about, but, like, just writing everything out helps. And that's exactly why I draw them out, just because I'm, more of a visual person. And if you are like that as well, then, by all means, go ahead and draw them out if it doesn't take too much of your time. And the last question that I wanted to talk about this is actually one of his favorite questions. So, because it's pretty comprehensive. It covers, I think, you have to incorporate a lot of information that you learned in this class just to do this one question. So he's asking about, so camel humps are containing fat, which they use to produce metabolic water. Now, metabolic water meaning water that's produced as a metabolic byproduct of something else. It's not like, it's not like they can use that water to directly drink. And so he's asking, if I've got a kilogram of fat, how much water can I produce from it? Because that, from beta oxidation, you're essentially able to produce water from doing that. Whether that's, from the process itself or, the downstream processes as well. And so he's talking about, the fat is all tristerylglycerol. And so we know that stearate is going to be an 18O fatty acid. And so we're going to run this through beta oxidation. Oh, and he told us not to worry about the metabolism of the glycerol, so we don't care about that. All we know is that like we're going to get 3 stearate molecules from this triacylglycerol. And the molecular weight is 890. We'll need that for the dimensional analysis as well. So when we run this through beta oxidation, since it's an 18 carbon chain, we're going to break it into 2s. So we've got 9 acetyl-CoAs. We're also going to make 8 NADHs and 8 FADH2s because there's no double bonds going on. There's nothing weird about it. So 8 NADH and 8 FADH2. And because this is beta oxidation, we're also going to lose 8 waters because you need to put water in to do this. And so we know from the citric acid cycle that for every acetyl-CoA we put in, we're going to make 2 H2Os. So this is going to be multiplied by 2. We're going to get 18 waters from our acetyl-CoA. Our NADH will directly give us 8, and so will our FADH2. And we're also going to lose 8 that we invested to do this. So we add these together. These will cancel each other out, and we're left with a net of 26 water per stearate. And keep in mind that we do have 3 stearates because this is a tri-stearoyl glycerol. So there were 3 attached here, so we're going to multiply this by 3, and we're going to get our final, production of 72 water per tri-stearoyl glycerol. I'm not going to write all of it out. Okay, so now we can actually do our dimensional analysis. And so what we have to do is we're trying to figure out how many liters we can get from this 1 kilogram of fat that we have. Now, how I would start thinking about this is if I have this I know that I'm making 72 moles of water for every mole of the tri-stearoyl glycerol that I have. And I also know that, I have the molecular weight, so I can multiply, that's going to be 890, grams per mole. So 890. What I did here is that, I just flipped the order of, it would normally be 890 grams of tri-stearoyl glycerol would be for 1 mole, and I just reversed the order to make the units cancel out because I eventually want to get to liters. And so now, I've got, I know that I have 1,000 grams of the tri-stearoyl glycerol from this 1 kilogram of fat. This is just over 1. And so now we've taken care of canceling out all of these things that tell us about the fatty acid chain. And so now we can just deal with the fact that we want to get to a certain amount of water. And so what we have now is that we know that for every 1 mole of water, we're going to get 18 grams of water. And then from what we have, we also know that, it's also 1 gram of water. That's going to be equal to 0.001 liters of water. And the way you can do that is, 1 gram is 1 cubic milliliter, and then you can go back from there. So it's 1 gram is going to be equal to 0.001 liters of water. And I think, honestly, this is the hardest part of that problem is going from being able to remember that you can go from grams to liters of water like that. But now everything, all of our units can cancel out, and we're left with just liters of water. So when we do all of this math out, what we get is that we're left with 1.5 liters of water that this camel is producing, from this 1 kilogram of fat. And that's it for this video. I do want to say thank you to you guys for, watching these videos this semester. Because, without you guys, I would just be some guy sitting in my room talking to myself about biochemistry. So I want to thank all of you guys. I wish you the best of luck on this final, and, it is a huge achievement to just have gotten this far, so you should all give yourselves a pat on the back, I think. Just keep working as hard as you have this whole semester, just for like these 2 more days that you've got before your exam. So yeah, I hope that these videos and the action centers were helpful to you this semester. And if you have any feedback on like how I can do this better next semester or anything like that, please feel free to comment or email me directly. But yeah,